Cool. Hello, everyone. How's everyone doing tonight? I think we can do a little bit better. How's everyone doing tonight? Woo! That's awesome. Are you all excited to learn some new physics? Cool. Well, I'm really excited to be here and talk to you. I'm going to be telling you a little bit about the work that I'm doing to search for new particles. Some of the techniques that I'm using range from state-of-the-art machine learning techniques to a special method in mathematics that was originally designed for moving dirt. Okay. But before all of that, I would first like to start with what my path as a scientist has looked like so far. And I guess to become a scientist, it requires a lot of school. And so for me, that has meant following my research interests in a tour around the UCs. I was an undergraduate at UC Davis, where I majored in physics and got a minor in mathematics, and did some research in particle physics using some techniques from machine learning. I then moved to Southern California, where I got my PhD in theoretical particle physics from UC Irvine, and I was doing research in particle physics using some state-of-the-art machine learning techniques inspired by that dirty math that I mentioned earlier. After you get your PhD, the typical path for a scientist, as we just heard from Mark, is to do what's called a postdoc, short for postdoctoral. And when I was trying to decide what institution I wanted to go to for my postdoc, KITP was the obvious choice, as it's home to some of the world's leading experts in machine learning, particle physics, and this special branch of mathematics designed for moving dirt. And this was really important to me because during my postdoc, I knew I really wanted to try to do research at the intersection of these three fields. And I've been here for a year, and I'm happy to report that in that time, I've had a wonderful experience collaborating with experts in these disciplines to do some profoundly cool science, which I get to tell you all about tonight. So I'm a theoretical particle physicist, but some of you may be wondering, what is particle physics exactly? But before answering what is particle physics, I'd actually like to start with a different question, which is, what is our universe made of? This question is simple to pose, yet rather difficult to answer. You might look up at the night sky and think our universe is made up of celestial objects like stars and cosmic dust. But in a sense, this is true, but is there a more fundamental description? You might look at yourself in a mirror and think, well, we're made of molecules, aren't we? Maybe molecules are the fundamental building blocks of our universe. But what are molecules made of? Atoms, your chemist friend says. Molecules are made of atoms. But what are atoms made of, you ask? Well, about 100 years ago, we learned that atoms are not the most fundamental building blocks of our universe. They're actually made up of small particles called neutrons, protons, and electrons. But it doesn't just stop there. Decades after that, we learned that neutrons and protons are also not fundamental. They're made up of even smaller particles called quarks that are glued together by the aptly named gluons. But you might wonder, are quarks the most fundamental, or is there something even more fundamental than that? Particle physics is this ever-progressing search for the most fundamental building blocks of our universe. Simply put, the goal of particle physics is to not only find these fundamental building blocks, but also describe how they interact with each other using math. Now, this all might sound very abstract and esoteric. Why would particle physicists like myself want to dedicate our lives to studying it? Well, The answer is that with a deeper understanding, we can make predictions about the future, given observations about the present. And what's more, we might be able to do the reverse, like a movie that we could play forwards and backwards. With this power of predictions, we could, from the observations of our current universe, infer what the universe was like seconds after the Big Bang. With this power of prediction, we can harness these systems to improve technology. Particle physics in particular has a very long history of doing exactly this. Radios, microwaves, X-rays, to name a few, were all made possible by a deeper understanding of particles and their interactions. And lastly, and perhaps my favorite reason, with this power of predictions, we can do things that we can't yet even imagine. Things that we will only discover if we let curiosity be our guide. The current description of particles can be nicely packaged into what we call the standard model. Now, some of the particles on this table might be familiar, like electrons, which orbit nuclei in atoms, or photons, which make up light. But even the unfamiliar particles on this table play a huge role in the world around us. For example, we've already seen how some of the quarks make up neutrons and protons. But the other quarks on this table make up similar objects called hadrons. These are like cousins to the neutron and proton. And some of these hadrons play very important roles in nuclear physics, for example. Another example are the gauge bosons, which make up which are responsible for nearly every force known in our universe. Photons are the carriers of the electric and magnetic forces, which we use every day to power all of our electronics. Gluons carry the strong force, and as we've already seen, they're responsible for holding together the quarks inside neutrons and protons. And W and Z particles are the carriers of the weak force, which is extremely important in nuclear reactions. For example, the W particle is responsible for the nuclear reaction that converts neutrons into protons, causing radioactive elements to become more stable. This is known as beta decay, if you've heard of it. You may have even heard of the particle in the center, the Higgs boson, which made a splash when it was discovered in 2012 at the Large Hadron Collider. Its discovery won the particle theorists who predicted its existence the 2013 Nobel Prize. Now, the Higgs was theorized for decades before this, and it was largely seen as the last missing piece tying the standard model together. So its discovery was a huge deal. It's also a very special particle. It's the only known particle of its kind. And it's responsible for giving nearly every particle on this table a mass. With these 17 particles, we can describe all that we and the stars in the sky are made of and more. But we're not done yet. We still cannot describe all of the contents of our universe. Experimentally, we've seen many observations that don't quite fit in the standard model. It's like we thought we had a good solution to a riddle, but then got clues that we weren't expecting and don't quite fit with what we thought the answer was. For example, all of the standard model actually only describes 15% of the matter in the universe. The rest is something called dark matter, which likely consists of one or more new particles not currently in the standard model. Another problem with the standard model has to do with matter. We know that matter is made up of particles, but we also know that in addition to matter, we should have antimatter, which is made up of antiparticles. And we know that when particles and antiparticles meet, they annihilate into energy, leaving no matter or antimatter in the process. We also know that very early in the universe was a sea of particles and antiparticles, which were meeting and interacting and annihilating. But there was a small imbalance in the rules of particles at this time, which favored the creation of matter over antimatter. This is why when we look out at the universe now, all we see are things made of matter. It's because matter is the only thing that survived this era in our universe's history. Now, the Standard Model can explain some part of this imbalance, but it falls short of what we observed. So this matter-antimatter asymmetry is yet another puzzle piece that doesn't fit in the Standard Model. A third problem with the Standard Model has to do with these particles here, called neutrinos. The Standard Model predicts that they should be massless, like the photon. But in fact, experimentally, we've seen many times that they, in fact, do have mass. So this contradicts one of the predictions of the Standard Model. In order to explain unexpected puzzle pieces like this, we need new particles and also a new model that can fit them. Even though when we look out into space, we can see the effects of new particles, such as dark matter, this only really tells us about their aggregate properties. But in particle physics, what we're really interested in is the individual properties of each particle. And these are very hard to infer from this aggregate behavior. What we need is, ideally, what we need is a more isolated and controlled environment. What we need is to be able to create them in the lab. But this isn't so simple. It's not like we know where they are and we can pick up a particle and put it under a microscope to study it. But fortunately, there is still a way. Thanks to Einstein, we know that we can convert energy into matter. And thanks to quantum mechanics, we know that anything that can happen, no matter how unlikely it is, will. Putting these two things together means that if we speed familiar matter up to very, very high speeds, giving them a lot of kinetic energy, and smash them together, there is a chance that we create some exciting new particles in the process. Sounds pretty simple, but this is no easy task. In order to produce new particles, we need to speed up familiar particles, like protons, to very, very high speeds, close to the speed of light. And to do this, we need huge particle accelerators. This is an aerial shot of the Large Hadron Collider's accelerator ring. And as you can maybe see in the bottom, it is nearly 17 miles in circumference. It's huge. It's so big that it actually sits in 2 countries at once. Part of it sits in France, while most of it sits in Switzerland. Once we have these particles up to speed, we need to force them to interact by colliding them together. But these collisions are messy, and in order to capture all of the debris that they produce, we need big detectors. From this information that's collected by these detectors, we can then try to reconstruct what happened at the initial collision. This is a picture of a portion of the Atlas detector. You may have seen it before, but just to note for scale, if you look at the bottom and in the center, that is a person. So these things are huge. We need these big accelerators, big detectors, big experiments because particles are pretty hard to create and find in the lab. This is in part due to the fact that particles are really small. the difference in size between a particle and you is about the same as the difference between you and the entire Milky Way galaxy. Producing these new particles in these collisions is also very unlikely. They're very rare. For example, a Higgs boson is only produced in every 1 billion collisions at the LHC, making the odds of producing a Higgs boson about the same as flipping a coin and getting 30 heads in a row. Particles are there and then gone in an instant, faster than the time it takes light to travel the width of a proton. And when they disappear, they transform into other more familiar particles, such as electrons and photons. And it's these more familiar particles that we actually see in our detector. So even if we do produce these new particles, we're not going to see them directly. We're going to see the remnants that they leave once they disappear. All of this means that the differences that we will see in the data from these experiments are going to be very subtle. This is part of what makes particle physics so difficult. In order to find new particles, we need to both produce them and extract them from the data. This is forgot a piece. So a recipe to produce more of them is to simply increase how many times we try. And this is pretty intuitive. Imagine you're trying to roll a 6 with a single die. Odds are that if you roll at least 6 times, you'll probably get a 6. And this is because the chance of rolling any one number on this die is 1/6. So if you try 6 or more times, you'll probably get 1. Analogously, if the odds of finding a new particle are 1 in a billion LHC collisions, then we had better look at billions of LHC collisions. I also mentioned that in addition to producing them, we also need to be able to extract them from the data. And the signatures are very subtle. So even if we do produce a new particle, there's a chance that we can't tell that we did. So we have to not only be good at producing them, but also identifying which collisions corresponded to creating new particles. It's like a scientific version of Where's Waldo, except there's no guarantee that Waldo is actually in the picture. Ideally, we would like to get from our current understanding of the standard model to a more complete model that can explain and incorporate mysteries such as the nature of dark matter. In order to do this, we need new particles, and we need to be able to both produce them and extract them from the data. To produce them, we need lots and lots of collisions, which usually means that we need to either improve our existing experiments or build better new ones. And while projects like this are currently in the works, they are technologically very challenging and can take decades of work by thousands of scientists and engineers. So in the meantime, it's prudent to ask if there's ways that we can make gains on extracting new particle events from our data, making the subtle differences more obvious. So you might be thinking, better data analysis tools that can extract subtle features from lots and lots of data effectively and efficiently. That sure sounds a lot like a job for machine learning. And you would be right. Machine learning is a very powerful data analysis tool that can be used on very complicated problems. And to see why this is, let's look at a quick example. Say you were given the task of classifying millions of images as either cat or dog. There's so many images that you don't really want to do this by hand, so you'd like to write an algorithm to do it for you. An algorithm is just a collection of code that will take in an image and give you back the correct label, either cat or dog. And to start you off on designing this algorithm, you're given a small set of examples of correctly labeled images. Where do you start? You would likely have a difficult time if you were trying to write this by hand. How do you write code that says what collection of pixels looks more like a cat nose than a dog nose? And more importantly, how do you write such code so that the size, breed, and orientation in the picture doesn't matter? Needless to say, this would be very difficult, if not impossible, even if you're really good at programming. Fortunately, with machine learning, you don't actually write the algorithm yourself. Instead, you have the machine learn it through a trial and error process. Repeating this trial and error process thousands and thousands of times is what we call training. And once the network has been fully trained, it will give you the correct relationships. So even though we don't know what the solution is, and we don't know how to find it, we can program the machine to discover it for itself. This is what makes machine learning so powerful. Machine learning techniques like this one have been adapted and applied to help us extract new particles from the data. There have been, in the past decade, hundreds of such papers successfully applying machine learning to help us extract more information from our data and find new particles. But this great performance doesn't come without a catch. State-of-the-art machine learning methods can sometimes be difficult to get them to learn the right relationships, difficult to understand the relationships that they do learn, and also difficult to quantify how much we can trust the predictions that they give. Because of this, it's prudent to ask whether there are other options besides machine learning to help us extract new particles from the data. One option is some dirty math called optimal transport theory. My work as a scientist at KITP is looking into what extent optimal transport theory can be used by itself or in tandem with machine learning to create a data analysis tool that is efficient, effective, but also interpretable. So, without further ado, it's time to get dirty. So let's take a break from particles for a second, and I want you all to imagine that you are a French military engineer in the 18th century, and you have been tasked with building embankments, which is just a sophisticated name for a sophistically shaped and strategically placed pile of dirt. In order to build this embankment, you need to move dirt from a nearby excavation site. And because it's the 18th century, you don't have any fancy machinery. So this has to be done one shovelful at a time. And because you're a very frugal person, you would like to do this as efficiently as possible, minimizing the overall amount of work that you and your troops have to do. So what are your instructions to the troops? How do you move dirt from one pile to the other, one shovelful at a time, in the most efficient way possible? Finding this optimal strategy, you're going to need to consider two things. Both how far each shovel of dirt has to travel, but also how much dirt you're carrying in each shovel load. This is because if you carry dirt further, you're going to be carrying it for longer, and so it's going to take more work. Similarly, if you carry more dirt at once, that might save you a trip, but it will be much heavier. And so it will also take more work to move it the same amount of distance. The optimal strategy is going to need to balance both of these considerations. Now, this story might have sounded a little bit silly, but it's exactly how optimal transport theory got its start. In 1781, Monge, a French military engineer who was building embankments, first posed this problem of whether there was an optimal way to move piles of dirt to build embankments. But it wasn't until more than 100 years later that this problem was given a proper mathematical description and solved. Even still, it wasn't until decades after that that there were some major advances that realized the utility of this setup in other disciplines. And from there, the study of optimal transport theory exploded. More recently, in 2018, it was the topic of a Fields Medal, which is the mathematical equivalent to a Nobel Prize. And today, we have seen an explosion of applications in economics, machine learning, the natural sciences, including particle physics, but also biology and chemistry as well, and much, much more. Simply put, optimal transport theory makes things better, easier, more robust. It's a really powerful tool, but why is this exactly? It's because, well, data is dirt. More seriously though, data and dirt are both representations of a mathematical object called a probability distribution. And optimal transport, given an initial and a final distribution, tells you how to transform from one into the other, one shovelful at a time. But it doesn't just tell you how to optimally transform one distribution to look like another. It also gives you an idea of the overall work that it takes to perform this transformation. If two distributions are more similar, it requires less work. So this actually gives us a notion of distance between probability distributions. We normally think about distances between points, like the distance between me and the back of this room, or between me and the front row of this audience. But it turns out that having a distance between probability distributions is a very powerful data analysis tool. And it also turns out that there aren't a lot of other good ways to measure this. So this is why optimal transport theory is so powerful. Back to particles. Ultimately, what we would like to do is know whether the data that we observe is due to just familiar particles or familiar particles with new particles mixed in. In order to figure this out, we simulate what the data would look like in both cases, either with familiar particles only or familiar particles and new particles as well. Now, just by eye, the pink and blue distributions don't really look that different, but I promise you they are, even though the difference is very subtle. So which is more similar, blue and gray or gray and pink? And how would you be able to tell? You might say, well, let's try doing what I did on the last slide and overlay the two and see which is more similar. You can see that the differences are very subtle, but what's even more problematic is that some of these differences are not meaningful at all. They're just due to random chance. And this is because particles are fundamentally quantum mechanical objects, so everything is due to chance. And these differences may or may not indicate the presence or absence of new particles in the data. Okay, so with all that background, what do you think? Yell it out. Pink, okay. Pink? Yeah, pink? Okay, well, you're right. That's awesome. Pink is the correct version in this artificial scenario. But it's pretty hard to tell, right? Yeah. So this was an artificial example, but it's actually schematically very similar to real world particle physics new particle searches called bump hunts. So in this artificial example, I set the probability of creating this new particle to be 1 in 400. But if you recall, several slides ago, I told you that the odds of producing a Higgs boson are 1 in a billion, making the odds of producing this fictitious new particle 2.5 million times better than a particle that we've already found. All of this means that the real bumps in real world data are going to be even more subtle than this. And for new particles, sometimes they're so subtle that this sort of strategy won't work at all. So we would like to be able to quantitatively say what is more similar, pink and gray or gray and blue. But even in this scenario, that's 2.5 million times better odds than real world scenarios, it's pretty difficult to tell. But with optimal transport theory, we can translate this statement into a statement about distances, which distributions are closer together. This allows us to do things like reason which distribution is closer. This is pretty analogous to how I can reason that since the distance between me and the back of this room is maybe 200 feet, but the distance between me and the front row is maybe 15 feet, that the audience in the front row is closer to me than the back of the room is. For distributions, optimal transport theory makes similar comparisons possible. But we won't just stop there. Combining optimal transport theory and machine learning does even better. It's more powerful than optimal transport theory alone, but it's also better behaved and more interpretable than machine learning alone. My collaborators and I, in the past year, have been applying these strategies to many different kinds of data in particle physics. And in some of these cases, we've actually also been going a little bit further and trying to inject some knowledge about the underlying physics into the math of optimal transport theory to improve performance even further. So we would like to find rare new particles. And finding rare new particles means we need better data analysis tools to extract subtle features from the data. Optimal transport theory, machine learning, and a combination of the two are promising candidates for such powerful data analysis tools. With these new particles, these will help us build a better, more complete standard model that can incorporate current mysteries like the nature of dark matter, why neutrinos have mass, and why there is something in the universe instead of nothing. Having this complete model is necessary to answer the fundamental question at the core of all of particle physics, which is, what is our universe made of? And as a scientist at KITP, I'm very excited to be able to help contribute to answering this question, even if it means playing a little dirty. Thank you.
Why did you say that there has to be antimatter?
We've seen antimatter. And also the underlying math that we have that has been proven true, at least to what we think, it comes out of the prediction from there. So it comes out of the predictions of quantum field theory that antiparticles should exist.
I'm curious, when you say rare particles, rare as in like there's not a whole lot of them, or rare as in you just like haven't identified them? I guess I'm curious why you're using the word rare.
Yeah, so the reason why I was using the word rare was kind of specifically in the context of producing them at these colliders. And yes, thank you for that point of clarification, because we know if we just look out in the galaxy, there's lots of dark matter particles floating around. We just can't figure out anything about them, or not much about them. It would be better if we can make them in colliders. But doing that, because they interact so weakly with familiar particles, is pretty unlikely. So that's why I use the word rare.
Thank you. Fascinating and very clear presentation. Where does gravity fit into this?
Good point. You caught me. Yeah, no, it doesn't. So I so I mentioned very, very early on in the talk that the gauge bosons describe almost all of the forces, but I neglected to mention the big glaring example, which is gravity is not currently in the world, or in our model of particle physics. I don't study quantum gravity, but there are lots of amazing people at KITP that do. But quantum gravity is trying to unite the world of particle physics with the world of gravity, as Einstein wrote down.
Could some of this methodology bring to light some of the mysteries about gravity as well?
Yeah, I'm not sure, honestly, but that's a great question. Yeah.
So I was thinking about the particle accelerator in France and Switzerland.
Yeah.
So you said there was, 1 in a billion chances for us to create a new particle when we smash two particles together. But how long does it actually take to do that? Because if you can just fire them off, if you can do 5 billion within a day, then you have, can you potentially find 5 new particles within a day, for example? Or what's the sort of timeline and resources that it takes to make those collisions happen?
Yeah, no, great. This is awesome. These were some details that I didn't weave into my talk, but this is an awesome question. So I guess one point is that these rare particles are probably even less likely than 1 in a billion. So they're even more rare than that. But yeah, you're exactly right. We're actually producing millions and millions of collisions every single day. But most of what's produced in those collisions are much more familiar processes. And so even though we can produce, or even though we have a lot of collisions running every single second, part of what's the actual limitation is the data write speed. So we can't write out enough data. And so there's actually a filtering system that happens at a very low level in the detector system that tries to filter out what are interesting events, or potentially interesting events, rather. And then there's further data analysis that goes on from there. But most of the data we actually produce is kind of necessarily not that interesting. And so it largely gets thrown away. But with those details aside, you're absolutely right. If you accumulate more collisions, that increases the likelihood that you will see a new particle. In particle physics, we call this luminosity, and it's usually a function of how long the experiment runs for, but it's usually measured on the time order of years. Yeah.
Thank you also for your presentation. That was really interesting and fun to watch. So I have a question about when you start to discover new matter. Do you anticipate that the new matter will be distinguishable from each other, and it will be very easy to tell them from apart, or the more matter you maybe discover, it's going to be difficult to tell them from apart from each other. I'm just curious about that, I guess.
Yeah, no, that's an awesome question. So, I think it depends a lot on what new particles you're looking for. I would say the field as a whole has spent a lot of time looking for dark matter, and so a lot of these theories are very well fleshed out. And there are a lot of theories that predict that there won't just be one new dark matter particle. There might be many. There might be an entire mirrored dark universe that looks more or less like ours. And yes, it's absolutely something that we would like to be able to do to distinguish them. But you're right, it's not always possible. But that is what we strive to do, I guess.